We've got a linear transformation T that maps from Rn to Rm. So my inputs are n entry vectors and my outputs are vectors that have m entries. Okay, so the question is, T maps onto Rm if the equation T of x equals b has at least one, at most one, exactly one solution. At least one, yeah. It just has to have a solution, right? If whatever b you put here, you can get a solution, that means that it maps onto Rm, right? It's the same thing as spanning the m Rm, yeah. Okay. So T is 1 to 1 if the solution Tx equals b has at least one, at most one, exactly one. At most one, yeah. At most one, okay. And it has to be both, want to be both 1 to 1 and onto, then that equation would have to have exactly one, because it would have to have at least one and at most one, so it would be exactly one. You can't give yourself a 5. So for today's lesson, we're going to talk about one-to-one and onto some more, and we're going to talk about finding the standard matrix of a linear transformation. Okay, but we're going to start with one-to-one and onto, and we're just going to talk about regular functions, like regular functions f that go from R to R, like something you would have studied in college algebra. And we're going to talk about one-to-one and onto. All right, so one-to-one, anybody remember how to identify a one-to-one function, like from college algebra? One input, exactly one output. How do you visualize that graphically? The vertical line test. Yeah. All right. So onto means that the range has to equal the entire codomain, right? So my codomain here is R. So if my range is all real numbers, then we would say the function maps onto R. So we're going to look at each of these separately. It might help to draw a quick sketch, like f of x equals 3x minus 4. That looks like a line like that, right? Is that one-to-one? Does it pass the vertical line test? Yes, because for each y, it comes from exactly one x. Is the range all real numbers? Yes, then it maps onto R. So this is one-to-one and maps onto the codomain. Yes. Yeah. So it goes from R5 to R. So that would not be one-to-one. No. Well, you can't really draw it if it goes from R5 to R, but yeah, if you have everything getting mapped to a single point, then there's a y that came from multiple x's, right? Which is the definition of not one-to-one, right? One-to-one, each y has to come from exactly one x. All right, so going back to R to R, let's look at x squared. Is that one-to-one? It doesn't pass the vertical line test. Oh, yes, sorry, I mixed them up. Sorry, the vertical line test tells you it's a function, and the horizontal line test tells you it's one-to-one. So A, it didn't matter because it passes both, right? But B, it does not pass the horizontal line test. So this is not one-to-one. It's a function, but it's not one-to-one. Not one-to-one. Is the range all real numbers? Right. So is it all real numbers? No. Right. So this is not one-to-one and does not map onto R. Horizontal line test. Horizontal line test is for one-to-one. I misspoke earlier. The vertical line test is to test if it's a function, and then the horizontal line test tests if it's one-to-one. Sorry. Yeah, so it doesn't pass the horizontal line test. So because there are two y's that come from different x's. So it's not one-to-one. Yeah. Sorry. Yeah. Okay, x cubed minus x squared. I could, but I don't really care. I just want to know what the graph looks like. So I'm just going to have my calculator give me a picture of it. Why doesn't it map onto R? No, that has to do with why it's not one-to-one. It doesn't map onto because its range is not all real numbers, right? The codomain is R because the outputs are all real numbers, but it doesn't produce every real number, right? Because the range of this thing is only positive reals. There's all these negative reals that can never be produced. So it does not map onto R. All right, x cubed minus x squared. Oops. 6. Looks like this. Maybe I'm going to change the window a little bit. Yeah, that's a little better. Okay, does it pass the horizontal line test? It doesn't. It's got a little bump in it. It's hard to see, but if I zoom in here a little bit, so let's change the window and make y go from like -1 to 1. It's got a little bump, right? So this is actually not 1-to-1. It fails the horizontal line test. But it does map onto R because every R is produced as a Y value. Every element of the real numbers is produced as a Y value. Its range is all real numbers. So this is not 1-to-1, but it does map onto R, right? Every Y value is produced as an output of that function. Every real number is produced. All right, e to the x, right? It looks like this. Does it pass the horizontal line test? Yes, so it's 1-to-1. Is every real number produced as an output of this function? No, you only get positive real numbers. So this is 1-to-1, but not onto, it doesn't map onto R. So it can be both 1-to-1 and onto. It can be neither, not onto, not 1-to-1. It can be not 1-to-1 but onto, and it can be 1-to-1 but not onto. Right? So there's no like rule that says that one occurs with the other or anything like that. All right, so the concept of 1-to-1 and onto kind of makes sense. 1-to-1 means that for any y, it can only come from one x, right? And onto means the range has to fill the entire codomain. All right, so now we're going to move on to dealing with linear matrix transformations. So for each of these linear transformations T, we want to find the standard matrix A and determine if T is onto and or 1-to-1. All right, so I know that T of 1, 0 is 2, 6, 3, and T of 0, 1 is 4, 0, 0. So T is going from R2 to R3 because my inputs are 2-dimensional vectors and my outputs are 3-dimensional vectors. Okay, so if I'm looking for a matrix A so that I have A times my input equals my output B. So I'm looking for some matrix A so that when I multiply by a 2-entry vector, I get a 3-entry vector, B1, B2, B3, right? Because my inputs are in R2 and my outputs are in R3. So this vector is 2 by 1, right? And my output vector is 3 by 1. Yeah, so what does my matrix have to be? No, 3 by 2. 3 by 2, right? Because my inner dimensions have to match, and then my results will be my outer dimensions of 3 by 1. So I'm looking for a 3 by 2 matrix, 3 rows, 2 columns. And then jump to a new page here. Okay, so I need a matrix here, 3 rows, 2 columns, and I need to multiply by 1, 0 and get 2, 6, 3. Right? And then I have to use that same matrix, whatever it is, and multiply by 0, 1 and get 4, 0, 0. Okay, so I got to figure out what goes in this matrix in order to get these results. What numbers should I put in this matrix? So remember, it's 3 rows, 2 columns. So I'm looking for like, I got to fill these in. Yeah, 2, 6, 3 and 4, 0, 0. Because if I put 2, 6, 3 here, then when I use the entries of the vector as a weight, I'm going to have a 1 on my 2, 6, 3 and a 0 on the second column, right? So then over here, I want to have a 4, 0, 0 in the second column because I'm going to put a 1 on that guy and a 0 on the first one. So my final matrix A has to combine those two. It's got to be 2, 6, 3, 4, 0, 0. So this is my standard matrix A. So if I multiply by 1, 0, I'll get 2, 6, 3. If I multiply by 0, 1, I'll get 4, 0, 0. Yes. So the 2, 6, 3 and the 4, 0, 0 came from knowing what happened to 1, 0 and 0, 1. And those vectors are special vectors, right? They are called, they are the columns of the identity matrix, yeah. So that's what you want to look for. I gave it to you in this case. If it's not given to you, you want to try to figure out where do the columns of the identity matrix get mapped to. The resulting vectors, put them together and they make your standard matrix. Yep, something like that. Yeah. Yeah, but typically it won't be that hard. Like it'll be easier to figure out where 1, 0 and 0, 1 go, or whatever dimensional thing it is. No. All right. Okay, so now the rest of the question, right? The rest of the question is find the standard matrix A. So I did that, right? Found the standard matrix. Then we want to determine if T is onto and or one-to-one. Okay, so we just talked about what one-to-one and onto are. If you're just going from R to R, let's think about it in terms of R2 to R3. Okay, so I want to see, is this one-to-one and onto? Okay, so let's think about onto first. So A is the matrix 2, 6, 3, and 4, 0, 0. All right, so T of X is A times X, right? And A is that matrix. So whatever vector I want to plug in, I just take that vector and multiply by A. Get a new vector, A times X. All right, so the question is it onto? So what's the codomain of this transformation? What size vectors does it produce? 3 by 1s. Okay, so my codomain is R3, right? So the question about being onto is if the codomain is R3, my question is the range R3? Can I produce any vector in R3 as an output of this transformation? Okay, so if you pick one, like whatever it is, B1, B2, B3, you can pick any vector in R3. I want to know, can I multiply A times some vector X You do get a vector in R3. If you multiply by 0, 0, you would get 0, 0, 0. Yeah. Okay, so A, is there a vector x1, x2, right? That can produce any given vector I want. Like you could give me any vector in the world, 10, 12, 17. Can I create 10, 12, 17? Can I create 32, 18, negative 7, right? Is there any vector in here that I can't create? So what I'm going to do is I'm going to use a generic B1, B2, B3 and see if I get a solution here, right? So if for any B1, B2, B3, is this consistent? Have I asked you this question before? Yes. When I was talking about spanning the columns of a matrix, right? So I'm asking, do the columns of this matrix span R3? That's another way of asking this question. Do columns of A span R3? And what do you look for when you're trying to answer this question? A pivot in every row, a pivot in every row. So I'm just going to pull up my calculator and row reduce matrix A, matrix edit A, and it's going to be 3 rows, 2 columns, 2, 4, 6, 0, 3, 0. And then matrix, oops, second matrix, math. Oh, I didn't know you could do that. RREF, matrix A. Invalid dimensions. Okay, so I think I'm going to have to, you can row reduce this by hand, but for some reason your TI tends to get stuck when there are not enough columns. There are more rows than columns. So I'm just going to augment it with like a set of zeros. So you can have a pivot in every row. In fact, I think you do. So that added a column of zeros. Okay. So yeah, oh yeah, I can't have a pivot in every row. You're right. You're right. All right, so A reduces to, A is a row equivalent to 1, 0, 0, 0, 1, 0, right? So there is not a pivot in every row. So this means it does not span R3. There will be a B1, B2, B3 that you can pick that would make this system inconsistent. Right? So there's not a pivot in every row. That tells you that T does not map onto R3. There is a vector B1, B2, B3 that you cannot create by multiplying A times a 2-dimensional vector. Okay. Good question. What about the one-to-one? So I need to show, remember that T of X, this is the function that takes an input vector X and multiplies it by the matrix A. And A, I'm just rewriting things we already know here, 2, 6, 3, 4, 0, 0. Okay. So we need to show that there is at most one solution to AX equals B. I have to show that for whatever B I pick, when there's a solution, there's only one solution, right? So I need to show that this has at most one solution, right? So 0 solutions or 1 solution, right, for whatever b I pick. So in other words, when this has a solution, is it unique? Is there only one particular x that can produce a particular b? So if I row reduce 2, 6, 3, 4, 0, 0 with a B1, B2, B3, you get, I'm not going to go through all the work, you get 1, 0, 0, 0, 1, 0, you already knew that part. But over here, you get B2 over negative 6. You get B1 over 4 minus B2 over 12. And here you get negative B2 over 2 plus B3. I just did the row reduction algorithm by hand so that I could see what B1, B2, B3 turn into. Right? All right, so does this thing have more than one solution? Is there one solution or infinite solutions? When a solution exists. Does it have a free variable? That's another way of asking the question. No free variables, which means there's one solution, right? When you have a free variable, that means you have more than infinite solutions, right? But in this case, there is not always a solution, right? This is only consistent if this negative B2 over 2 plus B3 equals 0, right? So that's why it's not onto, because of this thing, this last row here. But when there's a solution, it is unique, right? Because we know that x1 would be B2 over negative 6, and x2 would be B1 over 4 minus B2 over 12. So it's unique, exactly one solution. When there's a solution, it is unique. So no free variables. This tells us that when there's a solution, it is unique. That means T is 1-to-1. So T is 1-to-1. Great question. What would it look like if it was not 1-to-1? You'd have a free variable, right? Which means you'd have a column without a pivot, right? So because the columns without pivots are the free variables, right? So what showed me that this was 1-to-1 is that I had a pivot in every column. Okay, so that's a good thing to write down, right? 1-to-1 is equivalent to pivot in every column of A, right? Whereas a pivot in every row tells you that the function is onto. What else was it that we looked for a pivot in every column for? Anyone remember? No. It was the linear independence. The columns are linearly independent when you have a pivot in every column. No free variables. So this is the summary here. This is like super important, right? Have this on your note sheet for the next quiz. Have it on your note sheet for the test. This is a summary that will help keep a lot of things straight, okay? So if you have a pivot in every row of A, that tells you that T of x equals AX, the linear transformation, is onto. It tells you that the columns of A span Rm. It tells you that the matrix equation AX equals B has a solution for all possible B. It tells you that every vector B in Rm can be expressed as a linear combination of the columns of A. Right? So there are lots of questions that I can ask you that you can check whether or not they're true by just saying, looking to see if there's a pivot in every row. Okay? Versus if having a pivot in every column. That tells you that T of x equals AX, the linear transformation, is 1-to-1. It tells you that the columns of A are linearly independent. It tells you that when the matrix equation AX equals B has a solution, it is unique, which is the same thing as saying 1-to-1, right? And it tells you that the matrix equation AX equals 0 has only the trivial solution. That was the definition of the columns being linearly independent. Okay, so we have all these things. So however I ask you the question, it almost always comes down to, is there a pivot in every row or is there a pivot in every column? Right? Is how you'll answer it. All right, we've got one more example before the activities. So here I have a transformation T that goes from R5 to R3. So it says that T of any vector from R5 becomes a vector in R3 by taking x3 minus x4, that becomes the first entry, second entry is 6x5, and the third entry is 0. So I want to come up with a standard matrix and talk about whether or not this is 1-to-1 and onto. So my standard matrix you get by figuring out where the columns of the identity matrix go, right? So I would like to know, what is T of 1, 0, 0, 0, 0? That's the first column of the 5x5 identity matrix, right? What is that? So this has 5 entries, right? So I want an identity matrix so that each column has 5 entries. So the identity matrix is, it would be I5, which is 1, 1, 2, 3, 4, 0, 1, 1, 2, 3, 0, 1, 0, 0. The identity matrix is always a square matrix, one's on the diagonal. So I'm going to take each column of I5, plug it into T, see what I get as a result. The resulting vectors are going to be the columns in my standard matrix A. So in the first example, it was easier because I just told you where the identity vectors went. All right, so T of 1, 0, 0, 0, 0. So x3 minus x4. x3 and x4 in this case are both 0, right? So you get 0. 6x5, 0, because x5 is 0 here. And then 0. Okay. So the first column of my standard matrix will be 0, 0, 0. So then I got to do T of 0, 1, 0, 0, 0. That's going to be x3 minus x4 is 0, 6x5 is 0, and then the third entry is always 0. T of 0, 0, 1, 0, 0. x3 minus x4 is going to be 1. 6x5 is 0, 0. And then T of 0, 0, 0, 0, oops, 1, 0.
Sorry, I'm a little slow.
Yep.
My question is, so these values for the identity. Values for
yes. Yep.
So for the third iteration is
x3 minus x4. Yeah, I'm plugging into that. So I did 1 minus 0 got me 1. Yeah. So in this case, now x4 is 1 and x3 is 0. So 0 minus x3 minus x4 would be 0 minus 1, which is negative 1. 6x5 is 0 and 0. And then one more, T of the last column of the identity matrix, 0, 0, 0, 0, 1. x3 minus x4 would be 0. 6x5 is 6 and 0. Okay. So, yeah. Right, right. No, yeah. I probably won't give you T of 3, 2 and T of 7, 8 and ask you to figure out the standard matrix. I could, yeah. You just like you said, you'd have to set up a system of equations, right? You would set up it would be hard. I probably won't do that. Yeah. Okay, so this means that the standard matrix A is the columns that I got as the result here. So this first one would be 0, 0, 0, 0, 0, 0. The next one is 0, 0, 0. The next one is 1, 0, 0. And the next one is -1, 0, 0. The last column is 0, 6, 0. This is my standard matrix for that transformation. Okay, so now the question is it one-to-one and is it onto? So let's think about one-to-one. So I have lots of ways to answer this, like go back to the summary. Where's my summary? Way back. Here it is. Okay. So I'm asking about one-to-one. So I could row reduce and see if there's a pivot in every column, right? Or I could think about, are the columns of A linearly independent? So that one, I like that one for this particular question. Are the columns of A linearly independent? What do you think? Right, the third and fourth column are multiples of each other. And any set that contains a zero vector is not linearly independent, right? So one-to-one, we could equivalently ask columns of A linearly independent. We can see that they are not by inspection, just by looking, right? If I take 1, 0, 0 and I multiply by -1, I get -1, 0, 0. That's a linear dependence among columns 3 and 4, right? And because I have columns that are all zeros, right? I have zero vector. Anytime a zero vector is in the set, that set is automatically not linearly independent. So this is a no. Big ol' no. Yep. You're right, yeah. Or you could say, if I were to row reduce this, I couldn't possibly have a pivot in every column because I have more columns than rows. Yes, so I couldn't possibly have a pivot in every column. Don't even have to do the row reducing. Good. So it's definitely not one-to-one. And then the question of onto. So for onto, what is the codomain of this function? R3. Yeah, my outputs are all in R3. Okay. Can I produce every possible vector in R3? Why not? It doesn't have a pivot in every row because the bottom is always going to be all zeros. Yep. Yeah, the codomain is R3, but the range is not all of R3. Yeah. So the codomain just tells you what kind of things it produces. It produces things in R3, right? But it doesn't tell you the set of all things it produces. 1, 0, 0, -1, 0, 0. 6, 0. Okay, this can't possibly have a pivot in every row because we've got a row full of zeros. Okay, so this is definitely a no. The other way, no pivot in every row. So the answer is no, it's not onto. The other way we could have seen it is if you just went back to the original definition, x1, x2, x3, x4, x5. So t of any vector in R5 gives you x3 minus x4, 6x5, 0, right? The third entry of every output value, every output vector is 0. So there are lots of vectors that I cannot produce using this formula, like any vector that has a non-zero third entry, right? So for example, the vector 1, 1, 1 is not an element of the range, right? And for a function to be onto, the range and the codomain have to be the same. Yes.
So let's say it was like X3
Uh-huh. It would not be as obvious. You'd have to do something by like looking at the pivots. Yeah.
but because you have 3 variables, should you?
You'd have free variables if that was an X2 or something.
Yeah,
I don't know, because all of these rows would be different. So we would have to I'd have to do the problem all over again. Come up with a new matrix A and look at its pivots. Yeah.
so let's say there's a pivot in the first column.
Yeah.
And not the fourth pivot.
Which is the most that you could have, right? Yeah. So this, so if there's a pivot in every this for, sorry, I'm stumbling. For onto, we're looking, is there a pivot in every row? So it's possible with 3 rows to have a pivot in every row, with 3 rows and 5 columns. So if this was a non-zero, I'd have a different standard matrix A, and it would be possible that I could have a pivot in every row, and it would be onto. Yeah. Impossible that it could be 1-to-1, because you can't have a pivot in every column of a 3x5 matrix. Okay. Okay, so I think that's enough of me talking. You do some activities now.